Good morning, everyone. We are going to start chapter 11 this morning. The very last problem I was working on last time, if you go to the very end of the last lecture video, I showed the final solution for that very last problem if you were looking for the math behind that one. But anyways, we're going to start here fresh in chapter 11 today. Chapter 11 has 7 sections, so we're going to skip 11.7. My pen not working. So you can skip 11.7 in your reading of chapter 11. But the chapter 11's on liquids, and so in this chapter we're going to talk about liquids and intermolecular forces that are holding substances together in the liquid phase. If we think about gases from chapter 10, the idea is that we have non-interacting particles. So as soon as they start to interact at lower temperatures, as we start to approach the point where the gas is going to condense into the liquid phase, we have those intermolecular forces dominating, and then you can get a sense that the substances that have stronger intermolecular forces, if you imagine them as liquids, the liquid's going to take more heat, more temperature to separate. So substances that have stronger intermolecular forces are going to take a higher temperature to boil. Then if you think of substances that have really weak intermolecular forces, then their boiling points are going to be really low. They're going to turn into gases at a lower temperature. And so we're going to try to get a molecular view of gases versus liquids versus solids. We'll talk in a little bit more detail about solids in chapter 12, but we don't get too detailed into chapter 12. We'll spend probably not even quite a full lecture on chapter 12. So we'll just cover a couple details out of the next chapter instead of covering the entire chapter 12. In case you were thinking we have this lecture plus 3 more, we're only going to spend about 2 lectures or so here on chapter 11 and probably the remainder of that 3rd lecture on chapter 12, and then hopefully a lecture reviewing. Okay, and then so other details in this chapter are looking at some different properties of liquids. We'll look at surface tension and some other properties, and then we'll get into heat changes associated with phase changes. So what are the delta H's of a phase change for solid to liquid versus liquid to gas, and then look at vapor pressure and some phase diagrams to wrap the chapter up. So let's get our start here looking at a comparison of gases versus liquids versus solids. A group of elements, the halogens, kind of gives us a good view here because you can go from F2 or Cl2 that are gases at room temperature. So if we're looking at a sample of chlorine, chlorine is going to be a gas at room temperature. The particles are going to be well separated. If we had a container of chlorine, we would see a yellowish color. Chlorine's a yellowish colored gas, but we wouldn't see a liquid or solid phase at all for the substance. And the particles would be well separated from each other. So we'd have chlorine particles bouncing around the container of chlorine. But bromine, we see, does have a vapor. So if you look at a sample of bromine, you would see some vapors above the liquid, but you would see a liquid phase. You could see if you slosh the flask around that it definitely is a liquid. And Br2 is a liquid at room temperature. And so the particles are closer together in terms of a diagram. So the particles are getting a little bit closer together, so they're interacting with each other, but they're not frozen. And so if you then look at a crystalline solid of something like I2 or iodine, then you see a crystalline solid, then you see the atoms are much closer together. They're never in perfect no motion at all. So it's never that the I2 molecules are just sitting there, but they're moving around, but maybe very slowly relative to each other, where in the bromine sample, they're still able to tumble around each other. And so we see I2 is a solid at room temperature, bromine's a liquid at room temperature, and then chlorine's a gas. So gases, particles well separated from each other, really low density. Liquids, particles are near each other but not oriented in any specific fashion. Then once you get into a solid, generally the particles are going to adopt a more regular pattern, and they're going to be kind of locked in but not permanently locked in. They're going to still have some vibration still. And so you can get a sense here that, well, what is it that makes Cl2, Br2, and I2 different? Well, that's what we want to talk about in this chapter, is we want to introduce what it is that's different between the two. But I think you can reason just by virtue of their difference of properties that I2 must have the stronger intermolecular force. And so if you're looking at ranking the relative strengths of intermolecular forces, we can just take the idea of their trend of boiling points and see that chlorine must have the weakest intermolecular force, then bromine next, and then I2 has the strongest intermolecular force because I2 is going to take the most heat to melt, the most heat, the highest temperature to boil. And so this is just by virtue of I2's boiling point and melting point being the highest of these 3 means it has stronger intermolecular forces. So intermolecular forces are just proportional to the boiling point or the melting point of a substance. So the stronger the force of attraction, the higher those melting points and boiling points will go for a substance. Now, if you're thinking about the properties of Cl2, Br2, and I2 from chapter 8's perspective, are those polar or nonpolar molecules? So we're looking at Cl2, Br2, I2. Are these polar or nonpolar? Of course, they're nonpolar. So those molecules are nonpolar, meaning there's no polarity difference between two identical atoms. Neither one develops a charge. And so both those molecules or all three of those molecules are nonpolar. If we look at HCl, HCl has these built-in charges. We have these built-in positive and negative charges, where HCl is a polar compound. So HCl is polar. So it's going to have some built-in attractive force, generally that we think of as being stronger. We generally think that dipole-dipole force of attraction. We'll get into kind of the force that unites nonpolar compounds is going to be a little bit different than the force that unites polar compounds. But we get this positive, negative attractive force. We call this the dipole-dipole force. And that dipole-dipole force isn't found, like we don't have that force of attraction in Cl2, Br2, or I2 because they don't have those built-in charges. And so what the halogens have to do, or molecules like them, what they have to do in order to exist as a liquid or a solid is they have to somehow induce that dipole moment. They have to induce the charge in each other. So if we have two adjacent chlorine molecules that are adjacent to each other, and let's say we're imagining this at a much lower temperature than room temperature, where we know Cl2 would be a liquid or a solid. The idea is that these atoms here have to induce a dipole. They have to somehow shift their electrons in such a way that we induce a dipole moment and create charges, that we create a partial, say, positive and a partial negative charge to create that attractive force. So we have to induce this dipole moment where we create, where there isn't naturally in the molecule a shifting of the electrons to create that plus minus attractive force. So it kind of stands to reason that if some compounds have built-in charges, and we can think of having some electrostatic force of attraction due to having those charges, when we look at molecules that don't have those built-in charges, in order for them to have an attractive force, they have to somehow induce or create that dipole moment in themselves in order to experience that charge. And so that is one of the main forces that we're going to see, is that's what we describe as being the dispersion force. And so the dispersion force, sometimes we call this an induced dipole moment, or the induced dipole force. So it's where the substance has to induce a dipole moment in itself in order to have a force of attraction. And so this is the only force of attraction in something that's nonpolar. So if we look back at Cl2, Br2, or I2, the force of attraction that those molecules have is the dispersion force. And so they have the dispersion force, this induced dipole force of attraction. And generally, that's a pretty weak force of attraction. This is why N2 has a really low melting point and boiling point, well below room temperature. Over just about 200 degrees below room temperature is the boiling point of N2. And so, but now if you look at Br2, and if you go from the trend to Cl2 to Br2 to I2, we'll see this also mentioned on a later slide, that it must be better to be bigger. It must be easier to induce that dipole moment for substances that are bigger. That's why I2 would have the higher melting point than something like Br2 or Cl2. So we get an increase in that melting point trend. If you recall back in chapter 7, we noted that the halogens were increasing their melting points and boiling points from top to bottom, and that was important. There was something going on there. The thing going on there is that the dispersion force becomes higher with higher size. So if we have a bigger molecule, we'll see this in a lot more detail as we continue, but we're going to get a bigger induced dipole moment if we just have a larger molecule. So if we increase the size of N2, and we'll even see that we can increase the size by either just increasing the molecular weight, like instead of N2 have Cl2, or to go to Br2 or to I2, we're going to increase the melting point and the boiling point of the substance. We could also just have more atoms. We're going to see that just having the same weight but having more atoms instead of fewer atoms is also better. But there's other forces of attraction. Let's kind of start at the top here, talk ionic bonding. And we're thinking of just the attractive force between any two substances. Plus and minus ions probably have the strongest overall force of attraction. So if we think of the force that holds like lithium and fluoride ions together, that's our ionic bond, that's our lattice energy if you recall. But the ionic bond strength of lithium fluoride, if you remember, just the strength of that lattice was about 1,000 kJs per mole. was the energy holding a mole of lithium fluoride together. In order to melt lithium fluoride, look at how high the melting point and boiling point is. That's just an artifact or a detriment of just how strong that ionic force of attraction is in terms of how high these melting points and boiling points are for the substance. Metals also have a very strong attractive force. We'll talk about metallic bonding more in chapter 12, but metals generally, not all metals have melting points in the range of 1,000 plus degrees C, but a lot of them do. So metals can have a really high melting point and boiling point as well. But of course we know mercury is a metal and it's a liquid at room temperature, so lithium has a relatively low melting point. And then metals generally have the opposite trend. Like if you go down the alkali group, if you go from lithium to cesium, cesium's almost a liquid at room temperature. Its melting point's like 30 degrees C. Lithium's about 200 degrees C. So you get a decrease in the melting point of metals. Well, metals are exchanging charge. And remember with lattice energy, it's better to be lithium fluoride than like cesium iodide, because the bigger the plus minus charges, the further separated those charges are, the weaker that attractive force is. The same thing with metals, that metals are exchanging electrons among all the nuclei of the metals. It's going to be better for those metals generally to be smaller. So usually smaller metals have higher melting points. Beryllium has a really high melting point and boiling point as a result of its small size. And then, but if you then say, well, if you take covalent bonds, they can never be strong. Well, collectively though, they can be. If you take the structure diamond, diamond is just a three-dimensional array, so we've drawn the tetrahedral structure a fair number of times, but just imagine you have a tetrahedral set of carbon atoms, and that you keep doing this. I don't know if it makes sense or how clear this will be, but what diamond is, if you just imagine making tetrahedral carbons and just keep going with it in all three dimensions, and just imagine you have millions and millions of carbons that are all connected by these tetrahedral covalent networks of bonds. So you get a really strong structure that results from just having covalent bonds. So even though the one bond between carbon-carbon is still only about 350 to 400 kJs per mole, where the ionic bond's like 1,000 kJs per mole per bond, the carbon network is actually very strong, and you get a really high melting point and boiling point. So the covalent network carbon has melting points, boiling points well above 2,000 degrees C. So I wouldn't memorize these boiling points. I think the takeaway message here is that if you're going to have a substance that has covalent bonds, it's going to be much better to have a network of those bonds that grows in 3 dimensions, as opposed to just having one molecule here, and then you get an attractive force between those molecules. So the difference between diamond, why it's so high, and then if you look at something like CH4, is that the CH4 molecules just have the weaker force of attraction between adjacent molecules. So like methane's nonpolar, so methane's only going to have that dispersion force of attraction. So it doesn't have, there's no real strong force holding two methane molecules together like there is holding all the carbons together in a lattice structure of diamond. Okay, so the dispersion force is one of our intermolecular forces. We saw in HCl, it has the dipole-dipole force. So any molecule that has a dipole moment that we think of as being a polar molecule, then we can think of as having these dipole-dipole interactions on top of having dispersion forces. So what we're gonna be ranking for compounds is kind of getting a sense of what force of attraction does a substance have? Does it have just the dispersion force? Does it have the dispersion force plus dipole-dipole forces? Or does it also have something we call hydrogen bonding? We'll see a few more examples of this as we go, but whenever we have some really small atoms involved in polar compounds that are going to have attractive forces with each other, something interesting happens where for HF, if we're picturing, and we know that this is the probably the one molecule that involves non-metallic elements, so between like H and other atoms, that has probably the greatest separation of charge. So we probably get the greatest buildup of partial positive and negative charges because we're taking H, which is really on the nonpolar side of nonmetals, is about as low of electronegativity as you can be and still be a non-metallic element. And then you can take fluorine, which has the greatest electronegativity overall, so you get a really big electronegativity difference, meaning the magnitudes of charges here are really high. Made that look positive. I'm just trying to say the magnitude of these charges here are relatively high for something like HF, but then also those charges are on the smallest of possible atoms we could have. And so when you have adjacent molecules of HF, we're gonna see you get an especially strong attractive force. So because we're adopting relatively high partial charges on relatively small atoms, remember being small is good when exchanging charge, then we're going to get a strong force of attraction between HF. We're going to get a stronger force of attraction with HF than something even like HCl, because HCl doesn't have as high of charges, chlorine's bigger. So when we're exchanging charge, it's better for those ions to be smaller. So you can kind of see the give and the take here, where for dispersion force, it's better to be bigger. So substances that are bigger have a stronger dispersion force, but substances that are smaller with big charges on their atoms also then have a stronger attractive force. And so let's take a look here. This is showing us what it means to have a dispersion force of attraction. And I think what's being kind of mimicked here is helium. So if we're picturing helium, we know that we have 2 electrons on our atom. And so if we're picturing 2 helium atoms are adjacent to each other, in fact, helium is the substance that has the lowest melting point and boiling point. The melting point of helium is about 1 Kelvin. So, just a degree above absolute zero. And then the boiling point of helium is 4 Kelvin. You can actually have liquid helium. They use it in a lot of our chemistry buildings will use liquid helium to cool supermagnets that they use for nuclear magnetic resonance spectroscopy, NMR. It's how we visualize our molecules or understand a lot of different structures of molecules. But liquid helium below 4 Kelvin, I mean, that's about as cold as you can get for a substance. But you can think for helium, though, it must mean that it has the weakest possible intermolecular force any substance can have in its liquid phase, because it's so easily overcome by even just a modest temperature of 5 Kelvin. And so if you're picturing and thinking about the 2 electrons in adjacent helium atoms, so the idea would be that if you're just picturing the electrons spinning around the atom, one's here, they're just kind of in random locations around the atom. If you take another helium atom, its electrons are just randomly oriented. And so then if you collide 2 heliums, they just bounce off each other at modest temperature. As you start lowering the temperature, the issue is, can we get the 2 electrons to kind of simultaneously kind of like be on the same side of their nuclei and kind of stay there for a moment in time? Because if we do so, that's inducing a dipole moment. What this is doing is it's putting a negative charge on the one side and a positive charge on the other. And then we can get a small electrostatic force of attraction that's going to unite and link those atoms together. And so that's what an induced dipole moment is. It's the electrons kind of simultaneously shifting to one side of their molecules or their atoms, such that we can create some partial charges that, at least for some moment in time, can allow there to be an attractive force through electrostatic attraction. And so then that creates either through some force or through friction or just through that small little charge, maybe that little bit of static electricity that you can sometimes feel, that creates a little bit of an attractive force and keeps those atoms held together. Now for helium, we go to 5 Kelvin. That's enough energy for the electrons to just go back to random and they bounce off, and the electrons no longer coordinate their locations relative to each other. But this is the picture of creating, in this kind of slide here, showing the creating of some electrostatic forces of attraction through an induced dipole moment. Now, as you can probably imagine, if we had 10 electrons, if we had neon, wouldn't this be easier? So for neon to have 10 electrons instead of 2, we're going to more easily be able to shift 10 electrons around than we're going to shift 2 electrons around. So it's probably not going to be too surprising that if we look at the noble gases, that the noble gases from top to bottom increase in melting point and increase in boiling point, because they have more electrons as we go from top to bottom, and it's going to be easier to induce that dipole moment. We'll see even a graph on the next slide that will show us a couple different melting points of the noble gases, just to make sure that we see that having 10 is better than 2 in terms of inducing this dipole moment. For an argon, even easier to induce the dipole moment. But we're going to stay, like if you get all the way to radon, you stay a gas. So even radon's a gas at room temperature. Even though it's really big, it still doesn't have enough of an ability to have a strong attractive force to overcome room temperature to be a liquid or a solid at room temperature. Okay, so the slide here is kind of comparing a few things. There's a detail on this slide. I don't know why they're comparing it, so I'm going to make a slightly different comparison this slide's making. This slide's comparing neon and fluorine because they're next to each other in the periodic table. But the difference between F2 is there's two of them. There's just one of neon. So fluorine having a second atom that's about the same mass of neon is really important for fluorine having this higher melting point. So having that second fluorine is really good for fluorine because we're doubling that mass. So if you recall, having one atom that can try to induce a dipole moment, it's probably better to have two. So if we have two atoms, they're about the same size as neon, or maybe just slightly bigger, that would probably be better in terms of inducing a dipole moment. But we may also want to cross-compare substances that are comparable in atomic weight. So if we start thinking of atomic weight here, neon is about 20 AMU. So let's write in some AMUs here for the mass, the average atomic weights. F2 is about 2 times 19, so that's 38 AMU. Argon's about 40 AMU. Cl2 is about 71 AMU. It's 34.5 times 2. Krypton, I think it's 84 AMU. And bromine's 80 times 2. So that's about 160 AMU. And then just to make sure we're kind of comparing relative atomic weights, 131 for xenon. And then I2 is 127 times 2, which is 254 AMU. Okay, so now let's compare the substances that are relatively similar. F2 and argon are kind of interesting in that they're similar. But another combo that have similar atomic weights are Cl2 and krypton. Compare this trend here. Notice how much higher Cl2 is, even though it's a little bit lower in molar mass. So if you recall, the idea is that the ability to induce a dipole moment is going to be higher with more size, but we can have more size two ways, either through having a higher molecular weight or just by having more atoms. So if we have a krypton atom, krypton maybe looks like a sphere, so the ability to induce a dipole moment in another sphere is probably pretty low because our contact points are so low. Now imagine we instead have two atoms here and we're trying to induce this dipole moment where we have this extra contact distance between two molecules. So having now double the number of contact points where we can try to induce or shift our electrons around is going to make it easier for Cl2 to induce its dipole moment. So having two atoms with the same or comparable mass is better than one. Having four atoms would be even better. So if we can take these relative atomic weights of about 80 AMU and have 4 or 5 or 6 or 7, the more atoms we can have, the better, because we're going to have more contact points to induce that dipole moment. So one contact point worse, 2 better, 3, 4, 5, 6 even would be better. Now, another thing to compare is just the neon to argon to krypton to xenon. So as you go increasing in size of the noble gas, of course, the boiling point is increasing. So we're just looking at the boiling point increasing with that size. And then also F2 to Cl2 to Br2 to I2, you can see the same trend. So for these nonpolar, these atoms or molecules that are nonpolar, the only attractive force is that induced dipole moment. So being bigger is better. Having more atoms is better for the same atomic weight. And you can even kind of compare the 160 versus 130. Now, 160, of course, is a slightly higher molecular weight, but we also have 2 atoms. So you see a much higher boiling point above room temperature now for the boiling point of bromine. So we now have a liquid at room temperature. Iodine's boiling point well over room temperature. So really high for I2. So now it's going to be, ends up being a solid at room temperature. And so having more atoms is better than having fewer atoms for the same molecular weight, but having more size is better as well. And so let's look at branching. So we have different types of hydrocarbons, like for example, if you have C5H12, we probably from nomenclature hopefully remember that that's pentane. And so C5H12 is pentane. Now if I connect all the atoms linearly, which is pretty much from like when we looked at chapter 2 at naming, that's pretty much the only way we were thinking of naming this compound. There was a section that we didn't quite cover, or a topic in chapter 2 that we didn't cover on branched hydrocarbons, which is where if you imagine we took a central carbon and then just put CH3s off the carbon, that's an isomer of C5H12. Like the formula here is still C5H12. And so it's still an isomer of pentane. It's a compound that shares the same formula but doesn't have the exact same connection of atoms. If you've had a lot of chemistry, you might have heard the word structural isomer. So it's just structurally a different way of arranging the atoms, but with the same atom count. So both of these are C5H12 structures. So they have the same formula, but different structures. And so now, do you think if you're trying to have a strong force of attraction, would you rather have the straight chain version of this compound or the branched version of the compound? And just think about how we're trying to have the electrons in these atoms induce their dipole moments such that we create a charge difference. And I think you can see that it's going to be a lot harder for the branched compound to induce that dipole moment, and we're going to have a poorer connection because there's just less connection. So it's going to be easier because we have all these contact points here to induce our dipole moment, so we can create bigger positive and negative charges by virtue of just having more contact points. So more contact points are better than fewer contact points. We can get there by having a more straight chain structure, a less branched structure. So having less branching is better. So the boiling point here, 310 versus 280. So we get a higher boiling point. This means a stronger intermolecular force with less branching. And so branching is like where we have a kink in the structure, So having a point where you have a single carbon that has 3 or 4 CH3s off of it is a branch point. Another isomer of pentane would be if we have CH3s to a CH, and then that to a CH2, and that then to a CH3. And I think that should add up to 9, 10, 11, 12. So that's C5H12 as well. And so we would predict that this structure, which is less branched than this structure, but more branched than the straight chain, should be in between. So the boiling point here should be somewhere in the middle of these two. So you can kind of almost rank the more branching, the worse for intermolecular forces, the less branching, the better. Somewhere in between would be in between in terms of our intermolecular force strength. I didn't actually plan on this example, so let me look up, if I can quickly, try to see. So the boiling point is 28 degrees C in Kelvin. That would be 299 Kelvin. And right in the middle. So kind of right where we would have predicted it, kind of less branching. And so it's going to be less than the straight chain, but not as low as the fully branched neopentane. Don't worry about the nomenclature. You don't need to know how to name these different hydrocarbons, but just recognizing the branching is going to weaken the intermolecular force on the molecule. Now let's look at the dipole-dipole force of attraction. So the dipole-dipole force of attraction is the attractive force that we have in polar compounds. Now, a polar compound like this would still have a dispersion force. So if I'm looking at CH3CN, it still has a dispersion force of attraction, meaning we can still have the molecule try to induce a dipole moment in itself, but it also already has a dipole moment. So it has dispersion forces, and then it also has the dipole-dipole force. So it has the ability to have the attraction of the charges it already has built into itself through the polarity. So when we're looking at this molecule, we have CH3, C, triple bond to N, lone pair on nitrogen, and that it's the electronegativity difference between carbon and nitrogen that creates a partial negative charge on nitrogen and a partial positive on carbon. We don't see any kind of symmetry that makes this molecule nonpolar. We want to think a little bit about molecular polarity, where if we were even looking at something like CF4, remember how we would say CF4, its dipoles all cancel and it's nonpolar. So even though something like CF4 has some really strong built-in charges, it doesn't end up being a molecule that would have a dipole-dipole force. And so this molecule here would not have the dipole-dipole force. So no dipole-dipole forces for nonpolar compounds. You have to have a polar compound in order to have this dipole-dipole interaction. So you have to have a permanent dipole moment, a permanent charge in the molecule that allows there to be that attractive force between adjacent molecules. Now, if you then think of something like, we've mentioned this with like CO2, carbon dioxide has a polar CO bond, two of them, but they're opposing each other such that the molecule is nonpolar. So another example like CF4 is CO2, and the dipoles here cancel, and that's why one of the good reasons why CO2 is a gas at room temperature. It's a gas at room temperature because it doesn't get the sort of result of the polarity of the bonds because of how they cancel each other out. Two adjacent CO2 molecules, they don't get that strong dipole-dipole force of attraction. They have to resort and use the ability to induce a dipole moment in itself, which doesn't give it a very strong force of attraction, comparatively speaking, to a molecule like CH3CN, where CH3CN, I think we'll see its boiling point in a couple slides, but it's well above room temperature because primarily of this strong dipole-dipole force of attraction. So we have the positive and negative charges that are linking up to adjacent molecules because they already have the charges. So you don't have to induce the charge when you already have the charges, but then you can also still manage to induce the charges further. So that's why we say CH3CN still has a dispersion force of attraction on top of the dipole-dipole force. So when we're thinking of substances, everything pretty much will have the dispersion force of attraction. It just becomes a question of does it also have another force of attraction like a dipole-dipole force of attraction? And then also we need to see a little bit more detail of what an H bond is to talk more about hydrogen bonding. Okay, so let's compare some dipole-dipole forces. Dipole-dipole forces I think are a little bit tricky for you guys to compare right now because if I showed you some random molecules, you might have a hard time telling me and predicting which one's more polar. But this slide here is trying to show us that propane has essentially no polarity. So the C3H8 molecule, the bonds aren't particularly polar. The CH bond's not very polar. There's a lot of cancellation of dipoles, even if that bond were polar, just based on the geometry of the molecule. So the dipole moment's very close to zero, and we get a low boiling point as a result. So we only have the dispersion force of attraction here, but then we're going to kick for dimethyl ether. Now we're going to turn it on in terms of having some polarity because we have a central oxygen. We have two carbons attached to the oxygen. And so we're going to have a dipole moment, partial negative on the oxygen, partial positives on the carbon. And then the boiling point goes up a little bit as a result of having this polarity built into the molecule. So now we have the dispersion force plus dipole-dipole force. And then when we then look at the molecule acetaldehyde, one of the things you want to compare when you're comparing dispersion forces and dipole-dipole force, you want to compare molecules that are relatively comparable in molecular weight. So all these substances are about 40 AMU. If we just went to a larger hydrocarbon, like the dispersion forces are additive, and so you could look at something like hexane or octane. Octane's a liquid at room temperature. Octane's boiling point, I think, is above that of water. So you can have a strong dispersion force. You just have to have a big molecule. So when you're comparing and you want to say, can you rank order like boiling points? Can you rank order the relative intermolecular forces? We have to keep the molecular weights in check so that we're not really drastically changing the dispersion force. So all these compounds have similar dispersion forces due to having similar sizes and similar molecular weights. But the key difference here is that the polarity of acetaldehyde, where we have a CH3 to carbon, where we have a double bond to oxygen in terms of our structure, that this molecule turns out to be more polar. Now this is where I say, if I said to you on a test, is the ether or the aldehyde compound, which one's more polar? I don't know if you could have predicted that just based on their structures, but the key would be seeing that the dipole moment is higher for the acetaldehyde is kind of telling you that it's more polar. So the more polar we make that sort of functional group or that molecule with the same size, we're increasing the dipole-dipole force of attraction. We increase the boiling point as a result. So the dipole-dipole force is going to increase with polarity. So the more polar the compound with comparable size, the stronger the force of attraction. Having the nitrogen here, again, I don't think I would have predicted this. I think if I even had said to you guys, would you have predicted that the compound with nitrogen, where nitrogen is not as electronegative, that it actually ends up being the most polar? But the compound does have the highest dipole moment, so the highest polarity molecule has the greatest dipole-dipole force. So it has a really high dipole-dipole force, and it has relatively speaking, the same dispersion force. So more polar molecule has a stronger dipole-dipole force of attraction. The boiling point is even higher. So we're getting an increase in our boiling point because we have a dipole-dipole force. We have an even stronger dipole-dipole force for the acetaldehyde and an even stronger dipole-dipole force of attraction for acetaldehyde. So the key is that the dipole-dipole force, probably not so surprisingly, increases with increasing polarity. It's like I run out of room and I normally don't even write well to begin with. So just increasing polarity. And again, you may not always, like it's not going to always be the case. I can show you structures and you can easily predict if the polarity is going to increase. But where you can usually predict polarity increases is where I show you a nonpolar molecule that is clearly nonpolar, then I show you a polar compound that is clearly polar. And if they have comparable molecular weights, you know that polar compound is going to have stronger overall intermolecular forces and overall the higher boiling point. So even if you can't compare two polar compounds and tell me which one's more polar, you can generally tell me which molecule is polar, which one's nonpolar, and therefore know that polar compound has a stronger overall set of attractive forces. Okay, now when you then look at some of these molecules and then you say, well, the dispersion force goes up with size, the attractive force, though, for dipole-dipole goes up with polarity. What about for really small molecules like water? Something really interesting happens for water where we have two relatively small atoms of hydrogen adopting relatively high partial positive negative charges, and we get a really strong attractive force. So let's look at hydrogen bonding for a minute and kind of compare. This slide here is doing something kind of interesting in a way where what it's looking at is it's comparing all of the, from like carbon to nitrogen to oxygen to fluorine, all of their hydrocarbons. So taking CH4, NH3, H2O, HF, and then going down the columns. And it's comparing the melting point trends as we go from top to bottom. Let's start with the CH4, because this group here, we know for CH4, we know these are all nonpolar. And so just by virtue of the structures of these molecules, these are all nonpolar. So there's nothing going on with the polarity in these molecules. In other words, the whole trend's nonpolar. So why does the boiling point increase? So what we're looking at is boiling point versus the molecular weight. So as you go from CH4 to SiH4, SiH4 is bigger, therefore has a stronger dispersion force, therefore has a higher boiling point. Germanium H4 is even bigger, therefore has an even higher boiling point. Tin H4, even higher. So nothing too crazy going on here. This is the same trend as like F2 to Cl2 to Br2 to I2 increase with the same trend. Okay, so now if we then look at the next group, if we then look at NH3 to PH3, you can kind of see the thing we're trying to explain is why is this so high compared to PH3? So why is NH3 off the charts compared to PH3? Or if you then look at HF and water, why are they off the charts here? So why are these guys here so high? It's because they have something special going on. The thing that they have going on that's special is that all of the molecules in their trend, if you look from NH3 to PH3 or H2O to H2S, HF to HCl, all those molecules are polar. So we would be calling basically every molecule in the trends for these molecules polar, but these are the smallest. And the compounds that are polar that have the smallest atoms involved give them the greatest possible charges, and you get a especially strong attractive force. So what's really important for something like water is that because the electronegativity difference gives us the magnitudes of charges that are the highest of possible charges. If you compare this to H2S, sulfur has a lower electronegativity, so the partial positive charge on hydrogen for H2S isn't as high. So the positive charge hydrogen gets on H2S, not as good. So if you're comparing this to like H2S, similar structure, but the partial positive charge here is just overall lower magnitude, just because of the electronegativity difference of sulfur isn't as high as oxygen. And so then oxygen also ends up with a partial negative that's higher than it would be on sulfur. So sulfur is still a polar molecule, but sulfur is bigger, not as electronegative, so the partial positive negative charges aren't as pronounced. But then sulfur is just bigger. So having a bigger atom with less overall negative charge gives a neighboring molecule. So imagine you're another H2S hanging out over here, and you're having this attractive force here, and you're comparing how strong is that attractive force compared to that in water. So for water, it gets the benefit of having the higher magnitudes of charge, but then the atoms being really small. The O being small is the primary second feature that makes water special compared to H2S. So water's off the charts here, HF's off the charts, and NH3's off the charts because we have what we call a hydrogen bond involved. We have a hydrogen attached to one of the three most electronegative atoms that also are the three smallest atoms that the H atom could bond to. And so we call these three molecules here that they have the H bonding force of attraction. Now the H bonding force of attraction is not this bond here. That's a covalent bond. So the hydrogen covalently bonded to oxygen, that's not what we call the hydrogen bond. The hydrogen bonding force of attraction is right here. So the force of attraction between adjacent molecules is the hydrogen bonding force of attraction. And that only water, HF, and NH3 on this chart here experiences this particular force of attraction. So in order to have the H bond, we have to have hydrogen directly attached to N, O, or F. And only those atoms. And the reason why it's only those three atoms, if you look at H attached to chlorine, which is right here, there's nothing special about HCl. Notice that HCl doesn't even have a higher boiling point than HBr. So if you notice, these other molecules increase just because they go to increasing size. Like HCl, if it had an especially strong dipole-dipole force that we would think of as being something like an H bond, shouldn't it be higher than HBr? And if you even look at if you look at room temperature is right about here. So only HF goes above room temperature. NH3's boiling point is still even below room temperature. Even though it has this hydrogen bonding force of attraction, we say it has a hydrogen bond because it's higher than pH3. It has a trend that goes higher than pH3, and then pH3 isn't even higher than arsenic. So if you go to the next element down, arsenic H3 versus pH3, you just get an increase because you get an increase in dispersion force. So if you look in this range here, you get the increase just because you go to higher dispersion forces as you go to increase size. So there's nothing special going on here. Like none of the third row, SiH3, pH3, H2S, HCl, none of those are off the chart. There's nothing really special going on with those atoms because now we do have polar molecules still, but we just don't have the atoms that are small enough to experience those strong attractive forces like water, HF, and NH3 do. Now, another question could be, or another issue would be, well, why is water so high? Like, why is water with a less electronegativity difference, why is it higher in boiling than HF? So HF has a greater electronegativity difference. Shouldn't HF have a higher boiling point? But the issue is that water has two hydrogens. So it can form two hydrogen bonds per molecule. HF only forms one. So water, despite having maybe each of the hydrogen bonds being a little bit weaker than in HF, it has a second bond. You can also maybe argue that the second bond creates a bigger negative charge on O than F gets. So presumably oxygen could have even a greater negative charge than fluorine gets in HF, giving it a stronger bond as a result. So water is better because we have two possible H bonds. But then you could say, well, why isn't NH3 even better than water? Because it has three possible hydrogen bonding sites because it has three H's attached to N. Well, there's a give and a take at some point. The electronegativity of N must drop off enough such that we don't have then a weaker boiling point. So I don't know if you need to memorize this per se, but this just ends up being the boiling point trend that you can sort of reason out, but maybe not have predicted. So I think it's easier to reason out that water, two H bonds, relatively polar, a relatively electronegative O, even though not as electronegative as F, gives water a stronger force of attraction. But then you get such a drop off to N that you don't get a higher boiling point for the three NH3s and it ends up being lower as a result. But this trend here, at least, is worth noting that water, the stronger force of attraction than HF. Okay, so with all that, when we're trying to spot molecules that can have dipole-dipole forces versus H-bonding forces versus just dispersion forces, the idea is this. It's that if I'm comparing two substances that are comparable molecular weight, if one substance only has dispersion forces, that's going to have a weak intermolecular force. If I take the same molecular weight and have a molecule that can have dipole-dipole force, that's better. Going to have a higher boiling point, higher melting point as a result. But now if I can have a molecule of comparable molecular weight that can H bond, that's even better. That should have an even higher melting point or boiling point. But can we recognize the things that can form that strong intermolecular? So we're talking intermolecular bonds with H bonding. Do we get hydrogen bonding in something like CH3F? So when I see CH3F, I can think Lewis structure. I might want to sketch an actual geometry too. But I can write this Lewis structure. Of course, the bonds aren't really 90 degrees, right? They're really 109.5. This is really tetrahedral. So whether or not I sketch this as tetrahedral maybe doesn't matter for this example. But can there be an H bonding force of attraction between a second molecule? Imagine I have a second molecule here. What's this force of attraction between this molecule? How is this molecule attracted together? Do we have dispersion forces? There's always dispersion forces. So this molecule would have dispersion forces. Does it have dipole-dipole forces? Yeah, it is polar. So this molecule is definitely polar. And so this molecule does have dipole-dipole forces, but it does not have the H bond force because I need a H atom directly bonded to fluorine. I don't need there just to be a fluorine in the molecule. I need a hydrogen atom directly attached to that atom because that's what gives me the big electronegativity difference. And I need a hydrogen there directly on the atom that has a really high electronegativity so I can get a really big positive charge on hydrogen. My hydrogens are on carbon. There's really no big electronegativity difference there. The partial charges on hydrogen here aren't going to be high enough for this thing to have any kind of a special H bonding force of attraction. So no hydrogen bonding for A. What about B? Hydrogen bond? Yeah, so B is going to have hydrogen bonding forces of attraction because I have hydrogen directly attached to oxygen. So when I look at my structure for ethanol, obviously I have a hydrogen covalently bonded to an oxygen atom. Now that in and of itself is not the hydrogen bonding force of attraction. That's a covalent bond. This is an intramolecular bond. So the covalent bonds, these are all collectively intramolecular bonds. But the question is, what about the intermolecular bonds? That's where intermolecular forces come from. So the attractive force would be between an adjacent molecule of ethanol So think about this force of attraction here. That's the H bonding force right here. So this is the hydrogen bonding force of attraction. Is that force of attraction between the hydrogens and the oxygen atoms involved in molecules that are next to each other, the adjacent molecules. So the intermolecular bonding between two molecules where you have hydrogen directly attached to NO or F. And so that's our H bonding force of attraction. Now ethanol would also have dispersion forces and dipole-dipole forces as well, and the H bonding force. So we have all three intermolecular forces possible for something like ethanol. So ethanol has a, it's in that same range of about 40 AMU or so. I think it's 47 AMU or 46 AMU, somewhere around there. So it's on that same order of magnitude as that acetaldehyde example, and its boiling point, I think, would exceed all of those molecules on that chart because it has that H bonding force of attraction. So the idea would be if you're rank ordering boiling points, you have a substance that only has dispersion forces, lowest boiling point. I have a substance that can have dipole-dipole force of attraction, maybe something like in C. C has dipole-dipole forces, but no H directly attached to that O. I have the carbon atoms directly attached to the O atom here. So I don't have H bonding forces of attraction in C. So if I'm rank ordering the molecules, I guess I can't rank order these because I have two that are polar, and I don't know how to rank the difference between the two that are polar. But I would probably be predicting here that B has a higher boiling point than A, and B has a higher boiling point than C just by virtue of being comparably molecular weight, and then also having that H bonding force of attraction on top of the dipole-dipole and dispersion forces. So there's a lot going on here with looking at molecules, trying to picture if they have a dipole moment. If so, they can have a dipole-dipole force. Then if they have an H directly attached to an NO or F, they can also have the even stronger H bonding force of attraction. Now, another force of attraction that we see is the force between ions and water. So we call it an ion dipole force. We've talked about this a little bit. This is the whole solvation process of something like NaCl. So how is it possible to take a compound that has that strong lattice energy between plus and minus charges and dissolve it into water? Well, of course, it's that the charges are then being replaced by an attractive force with water. So we're not losing the overall force between the plus and minus between Na plus and Cl minus, because we're regaining a new force of attraction between those ions and that of water. So of course it's the hydrogen's positive charge that surrounds the negative chlorine. We mentioned this all the way back in chapter 4, when we were first talking about ionic compounds dissolving in water. And then it's the negative end of water that surrounds the positively charged sodium ion. So we get these ion dipole forces. So we need, in order to have an ion dipole force, we need to have ions, and then we need to have a substance that has some built-in polarity to it. So we need to have a molecule that has a dipole moment to have this ion dipole force. And so the ion dipole force, you can imagine, this is going to be stronger if the ions have stronger charges. This is going to be stronger if the molecule has higher partial negative and partial positive charges. So what we want in order to have strong ion dipole forces is high partial charges and then high charges here. So we want these charges to be of the highest possible magnitude to have the highest charges. So we want the charge magnitudes to be high for our ions and for our solvent here. Now, water is good because it does have relatively high partial negative and partial positive charges due to being able to form those H bonds. And so we do have a good ability to form ion dipole forces between water and a lot of different ions, as we've seen back in chapter 4. So when we compare intermolecular forces, when we're looking at noble gases, substances that are atoms at room temperature, so these are pretty much just the noble gases, that they only have the dispersion force of attraction. That's why they're all gases at room temperature. There's some prediction. I've seen people arguing, there's been papers on, like oganesson is the noble gas that would be rated underneath radon. You don't see it on our periodic table because the periodic table is just old. Oganesson, I believe, was discovered only about less than 10 years ago. But its discovery is the synthesis of like a couple atoms in a weird chamber where they collide particles together. So it's never really synthesized in a great quantity, but it's actually predicted to be a solid just based on its size. So it's predicted that it's big enough that it would actually be a solid at room temperature, at least a liquid at room temperature, kind of showing as you go to a larger and larger noble gas, you are increasing those dispersion forces. So the only reason, I guess, we don't see naturally occurring noble gases that are liquids or gases at room temperature is because the biggest one we get to is radon, which is just still too small to have that strong enough dispersion force of attraction. Nonpolar molecules only also have the dispersion force, but if we look at nonpolar molecules, they at least have multiple atoms. So we can have, as we have more atoms with a comparable molecular weight, we get a higher boiling point. So we do see a lot of nonpolar compounds actually have a strong enough dispersion force to be liquids or even solids at room temperature. I2 is a good example. It's a solid despite only having the dispersion force, but it's because it's 250 grams per mole. It's a really big molecule. So being bigger is better in terms of intermolecular force for nonpolar compounds. For polar molecules, it's better to have small atoms because they give you a better or higher electronegativity, and then they give you higher magnitudes of charge. So polar molecules, you get a higher dispersion force, you get a higher dipole force of attraction, overall higher melting point or boiling point for comparably molecular weight substances, having the H bonding force even better. If you're trying to describe the intermolecular forces present in like a sodium chloride AQ sample, so if you're saying ionic solids dissolved in liquids, I've never understood why this chart doesn't check mark these other two boxes. I think if you look at anything that has dipole forces, if you're looking at anything with water, it has to still have dispersion forces and H bonding forces. I think this chart was looking at the force of attraction just between the molecule and the ion. But if you're trying to describe the forces in like salt water, I would say it has all those forces. The one thing I wanted to kind of leave with today is just this slide here that kind of compares a bunch of different molecules that are all fairly comparably sized in terms of molecular weight. So all the molecular weights on the slide are in the range of about 160 to 200 AMU. And so on the smaller side, we see radon, xenon. Those are gases at room temperature because we just have a single atom. Having 2 atoms is better, so 160 AMU, better for bromine. But if I could take, instead of Br2, notice that its molecular weight is 160, but its boiling point is 60 degrees C. So it's not like its boiling point is that high. Look at dodecane. Dodecane has now CH bonds, but it has a molecular weight of 170, so about the same overall molecular weight as bromine, but its boiling point is about 3 times higher, or at least in terms of degree C temperature, it's 3 times higher. So a lot higher boiling point because we have more atoms, more contact points, higher dispersion force. But then if you said, well, how about we change a molecule to something at H bonds? That's a sugar. So sugar has all those hydrogen bonding sites, so we get a comparable molecular weight with a bunch of H bonding and dipole-dipole forces. Water is melting at 150 degrees C and decomposing and caramelizing. It would boil at a much, much higher temperature if it could exist and not just decompose before then. So just one last slide for today here, and then we will continue on forward on Monday. All right, guys, have a great weekend.